Well, good afternoon, good morning, or good evening, wherever you may be joining us from around the world. Welcome to the third in our series of OpTek webinars. Today's session is titled Laser Processing of FAUs, Fiber Optic Array Units. Before we begin, just a quick note. Today's session is being recorded and there will be time for questions and answers at the end. You can submit your questions at any point during the presentation using the question box at the top right-hand corner of your screen. We'll gather those and address as many as we can in the final segment. My name is Alan Coleman and I'll be your host for today's event. I'm the QSHE Director and UK Site Lead here at OpTek. My background is in the semiconductor industry, both in the UK and internationally, where I focused on equipment engineering, sales and commercial development. More recently, I served as QSHE Director at a hand tracking and haptics company based in Bristol. Before we get into today's topic, let me give you a brief overview of OpTek, who we are and what we do. OpTek is a global provider of precision laser processing solutions. Our headquarters are in Abingdon, Oxfordshire, and we operate internationally with offices in Greenville, South Carolina, Boston, and Dongguan, China. Machine builds and micromachining and R&D take place in Abingdon, while our fiber center of excellence is based in Greenville. In Abingdon, we develop and deliver custom laser-based processors and systems to machine an extraordinary range of materials, from ceramics and polymers to delicate organics. If it exists, there's a good chance we can machine it. Our roots are in optical fiber processing, machining end faces, stripping, cladding, and other precision tasks that enhance yield and optical performance. Our expertise extends much further. We work across the full life cycle of laser processing, offering on-site services and helping customers transition from R&D and prototyping to full production systems. We often work on sub 300 micron features and provide a clear path from process development to bespoke automated systems. These range from compact desktop units to multi-ton, multi-laser 5-axis platforms, the largest of which weighs 7 tons and operates with sub-micron precision. Our Greenville, South Carolina site is home to our fiber center of excellence, where we focus on advanced fiber optic processing and assembly. The team there develops and delivers precision processes for stripping, cleaving, lensing, and splicing optical fibers, as well as fabricating and aligning fiber optic arrays. Greenville also supports process development, prototyping, and production for customers across telecom, medical, defense, and sensing markets, while providing local system integration, training, and technical support for our North American clients. Being part of a financially robust Humanetics group allows us to take on long-term, high-impact projects. We're also proud to hold certifications including ISO 9001, 14001, and in our UK and China facilities, ISO 13485 for medical applications, underscoring our commitment to quality and sustainability. Today, we're diving into laser processing of FAUs, fiber optic array units, and I'm delighted to introduce our speaker, my colleague Duane Dinkel, CTO at OpTek Systems. Duane will walk you through some of our most exciting advances and capabilities in this space, and I'll rejoin you at the end for the question and answer session. So, without further ado, over to you, Duane.
Fantastic. Appreciate the kind introduction, Alan. So we're going to spend a couple of minutes talking about what we do, OpTek's background, what we're good at, the business flow, and then we're going to dive right into FAUs. So I hope this is beneficial and enjoyable for all. So OpTek's fiber business consists of contract manufacturing and equipment builds. The contract manufacturing is done out of Greenville, South Carolina, and Dongguan, China. Abingdon, UK does some contract manufacturing as well. All of our equipment builds are done out of Abingdon. They're shipped all over the world. We have hundreds of systems in the field that are processing optical fibers. Our fiber processing brands are Laser Cleave. These are cleaving and lensing systems, laser-based, and Laser Strip. These are systems for removing buffer. So OpTek's core competency, I guess, goes back 20 years ago. We were building lensing machines, and these machines were basically modifying the tips of optical fiber, could be single mode or multi-mode, in order to couple the fibers to active and passive devices. We got pretty good at that. Throughout the 25 years, we can manipulate spot size, we can shift waste location. So, you know, these systems were ideal for preparing fibers for free space, receiving and transmission against active devices. So again, the core competence is laser lensing. That got us into laser cleaving. And then over the years, we developed various value add capabilities. We got into hermetic sealing, where we're using glass frits and metallic solders for creating hermetic seals for feed throughs. Most of that work was done through induction soldering. We then got into end capping in kind of a big way, taking optical fibers, attaching coreless fiber or graded index multimode fibers, cleave to a quarter pitch to achieve collimation or manipulation of numerical aperture or mode fill diameter. So end capping remains a big part of our business today. 5 years ago, we got into fiber array units, and we'll be talking about that at length here shortly. We're a turnkey provider, meaning that we provide AR coatings, we provide mirror coatings, fiber black gratings, and OEM-specific packaging is really the output of OpTek Systems. So we do rely on intelligent manufacturing. The majority of our systems are laser-based, and that includes lensing, cleaving, and stripping. And we are a relatively high volume contract manufacturer. We run off 2 shifts a day. We ship anywhere from 5,000 to 10,000 parts a week. And we also have development centers across, really across the globe, in Duane in the US, as well as in the UK. So OpTek relies heavily on novel processing. Central is going to be laser processing. It's non-contact. The processes are operator independent, meaning operator training, technician training is easy, and we can run product across 24 hours without downtime. The non-invasive laser processing also provides high reliability. Probably most important, it's design enabling. We can achieve designs on end faces that you really can't achieve mechanically. So we take a lot of pride in that. On the laser end face preparation, we do conical lensing. It's ideal for LEDs and any device that requires a circular far field. We make cylindrical and biconic lenses, which are great for elliptical profiles that you can find in DFB-based diodes. We manufacture ball lenses. The ball lenses are great for rapid divergence or convergence, as well as for collimation. And then, our bread and butter is flat and angle cleaves. So, angle cleaves for back reflection control, for TIR applications or side firing applications, and also on laser stripping. So we're able to strip both acrylates and polyimides. The stripping process it's fast, it's reliable, it's gives us high strength. So arguably, the majority of the world's coupled fibers are are probably going to be manufactured at some level with OpTek laser technology. Still talking about kind of who we are. Our toolbox consists of hermetic feed-throughs. These are, again, glass frits, metallic solders that are going to be induction soldered into various ferrules, and that is going to be inserted and soldered into our customers' snouts. We do a lot of end capping. The end capping is that controls energy densities. We can achieve collimation through quarter pitch grin attachment. We do a lot of PM alignment. A lot of the product that goes through our doors are going to be polarization maintaining, and so we're quite sufficient at proficient at maintaining strong PER end to end. We do have patents in high temperature probes, 700 degrees and above. These are comprised of proprietary composite chemistries as well as sapphire. Again, most of the high temperature work has some sort of a patent behind it. We make OEM specific packages. The device that you see here is basically a transmitting single mode fiber and a ball lens for receiving. That's just one of hundreds or thousands of OEM specific packages that we have. Fiber delivery is a big part of what we do for everything from lithotripsy and biomedical to the industrial applications. So fiber delivery packages are a strong suit for OpTek. All right, so diving into FAUs, the spirit here is that most of the audience, I think, has some sort of acquaintance with FAUs. This is not a PhD level dissertation by any means. But it might be a little bit above 101. The central theme of the webinar is going to be manufacturing. So bear with us. So FAUs are 1 or 2 dimensional arrays of optical fiber that are seated in a substrate. The industry kind of settles on silicon or silica or borosilicate diced substrates. They can also be used in flexible circuits. FAUs aren't new. They've been around for 30 plus years in the telecom industry. They were an enabler for DWDM manipulation in telecom architectures. Those were and are still called PLCs, planar light wave circuits, and array waveguides. They're used throughout multiple industries outside of telecom. You're going to find them in guidance systems and beam combining and aerospace applications. They're used today in quantum computing. On the medical side, they're used in beam delivery, and then also you'll find them in sensing. So FAUs have been around for 30 plus years. So why is OpTek even interested? Why are you attending this? So in the world of AI, FAUs are kind of finding renewed growth. AI, as we know it, is artificial intelligence. In the industry, we're not there yet. We're building data centers. There's a massive build out of data centers currently. Trying to achieve artificial intelligence. At this point, it's still an infrastructure struggle. So we're really referring to AI in the form of advanced infrastructure deployment. So, the challenges of these data centers is energy. A typical data center is going to require 40 terawatts of power or more. you know, you've got Microsoft out there buying 3 Mile Island in order to achieve, you know, in-house nuclear power at their disposal. You know, in the state of North Carolina, there's grid issues with further data center deployment. So a lot of issues with energy. It's become almost more of a thermodynamic constraint than anything else. Also on the fiber side, the infrastructure is constrained. You know, data centers today, primarily multi-mode, migrating towards single mode for longer stretches. The amount of data passing through these AI-centered data centers is staggering. So we're finding more and more fiber array units able to both handle the miniaturization requirements, but as well as the terabyte transmission requirements. So you know, AI is certainly tied in with chip development. So you know, you see the Broadcom, you see the NVIDIA, Intel, you know, all of the chip development, and to bring that into the data center requires FAU infrastructure. So the configuration of an FAU, how it mounts or interfaces to the waveguide is critical. And unfortunately, it's far from standardized. Up to this point, historically, PLCs, AWGs, these are all flush polished with the idea of butt coupling directly against a waveguide. That's the industry standard that exists just de facto. These are interfaced typically with index matching epoxies, and that's kind of the constraint today. So OpTek got into FAU production 5 years ago with protruding fibers. So we're laser cleaving the tips of protruding fiber. They can be direct mounted. You can still epoxy them for flush mounts, but they also accommodate free space transmission. Then we started getting into, well, we can't rely on the natural NA of the fiber to get good coupling into the waveguide. So we got into lens production, where we're actually creating lenses on the ends of the FAUs. Again, ideal for free space, ideal for spot and waste manipulation, so you can get better coupling into the waveguide. And then taking that a step further, we got into ball lensing, where we're actually able to achieve collimation. And that's gaining a lot of traction. You can put a small ball lens on the end of these fibers, so now you've got a collimating beam directly into the waveguide. And then some more sophisticated advances are taking these protruding fibers and we're in-capping them with coreless fiber. Some may have graded index multimode fiber, where we're able to, again, further manipulate both NA and mode fill diameter, but you're also able to achieve board mount configurations where they're side firing into the boards. So great for TIR applications. So the configurations that we've got here are at this point fiber agnostic. Some of the fibers are single mode, some are polarization maintaining. The chip designs currently are all over the place. There's, you know, some have circulators and isolators, some are polarization sensitive. The vast majority of the transmission legs are going to be polarization sensitive. You know, so at the end of the day, what you run into are many of the FAU configurations are, in order to accommodate the various chip designs, are going to be using transmission and receiving elements that are combinations of all of these different configurations. So that's one of the challenges that we have today. So much of the previous introduction is going to apply to our FAU manufacturing. We're relying heavily on laser processing. Most of our FAUs are hermetically sealed at some level. There's significant end capping at the FAU level. We're even finding fiber bright gratings are now being incorporated into FAUs, and of course coatings, where back reflection or mirror coating demands are required. So we do have dedicated manufacturing centers in-house to handle all of this FAU production. So further on the FAU contract manufacturing, again, the devil's in the details. So again, stress rod orientation, critical. Tight coplanarity, particularly if these are protruding fibers, absolutely critical. High coupling efficiencies, reduced alignment sensitivities for our customers, and we're able to utilize all of these coupling options that we just talked about to achieve these requirements. Okay, talking a little bit about our manufacturing flow. So we already talked about polarization maintaining fiber. Virtually every FAU that we manufacture today has a leg or multiple legs that are polarization maintaining. Stress rod alignment is critical. We've struggled for years, starting with the polarization maintaining aspect, tweaking, aligning under magnification. And we've really developed a pretty elegant solution for the stress rod alignment. Once aligned, that could be fed into ribbonization processes to lock the alignment into place. We heavily utilize laser stripping. Precision stripping presents a clean fiber that can be dropped and seeded into V-grooves. The fibers are lensed, they're laser cleaved, and then characterized. So taking a little bit of step into some of our manufacturing details. So we do start with the stress rod orientation. We believe that that's one of the most fundamental keys in today's AI driven FAU demand. So we do have, we start with the receptacle. What I have illustrated here are just simple MTPs, but you've got a receptacle that's going to receive a fiber, and through a combination of laser processing and alignment techniques, we're able to take an unoriented fiber at the multi-fiber level, orient the fibers, lock them into place, into the receptacle, and really once that's locked into place end to end on the assembly, then you're really off and running. These receptacles, if it's an MDP, it's more than likely going to be utilized in the application. If it's an in-house receptacle, it's sacrificial. It'll be lopped off later on down the road. But at this point, it's holding the fibers from a completely unoriented PM state to a fully oriented state. It could be in a slow axis, it can be in the fast axis, whatever's required. It can be even in a 45-degree axis. So once the fibers are ribbonized, or once the fibers are oriented, they're then ribbonized end to end. Again, both sides of the structure is going to be PM aligned. In reality, there may be half the fibers are PM, half the fibers are not. Some applications, 100% of the fibers are PM. So it's pretty much all over the place. But this is key. Once the fibers are stress rod aligned, once they're ribbonized, then you've completely demystified FAU production. At this point, you can process the fibers, drop them into V grooves. If you need to drop them into an MTP, if it's not in an MTP, you can do that. So it really demystifies the entire FAU production flow. So following the ribbonization, OpTek uses laser stripping techniques. Laser stripping gives us nice, sharp fibers. It's an ultra clean fiber. It does not have to be run through an ultrasonic bath or swiped with IPA. All of those things are just going to add to the embrittlement of the fiber. At this point, we're able to strip to tolerances within several microns. So it's a very high precision, very rapid process, our laser stripping. So once the fibers are stripped, they're clean, they have high tensile strength, and they're just simply dropped down into the V grooves. We use multiple epoxy chemistries for the lid attachment, for the landing. If they're polarization maintaining fibers, then we're using low stress epoxies. These are all just standard industry knowns. I'm sure you're employing something similar. The fibers at this point will be protruding 1 to 2 millimeters beyond the V groove face for subsequent cleaving. So then we use automated cleaving, laser-based cleaving to cut down to the desired protrusion. It may be 258 microns, it may be 900 microns, it's all over the place, nothing standard. If we are going to flush polish, we're going to cleave as close to the silica V groove face as we can, in the spirit of minimizing our polishing steps. If the fibers are lensed or end capped, slightly different process. They're going to be aligned prior, obviously prior, during the seeding operation, the fibers are precisely aligned to within 5 microns. So at this point, the fibers are being carried through the entire process on a common fixture. In the world of fiber manufacturing, handling needs to be minimized. So you also want to be as gentle on the fibers as you can. So once the fiber is fixtured, you really don't want to take it out of the fixture. So going all the way back to the PM alignment stage, we're sharing the same fixture. And when it gets up to the final inspection step, you know, the same fixture is used. Introduce the fibers into interferometry or visual interface inspection. We're also monitoring beam transmission, skew, unnecessary divergence. These are all necessary to quantify to avoid excessive losses. Insertion loss, return loss, polarization, extinction ratio, these are all monitored, as well as the physical dimensions. So that's kind of a walkthrough, simplification of our process. Looking at the next steps. So V-groove pitch today is really designed around 125 micron fibers with 250 micron buffers. So your current pitches are 250 micron to 127 micron. With the support of our sister company, FiberCore, we are aggressively pursuing 80 micron pitched V-grooves. We believe that this is going to be well received into the marketplace. Again, it's one step further into the miniaturization demands of AI. And we're also, today our manufacturing is limited to one-dimensional arrays. However, the process will also accommodate two-dimensional arrays. So those are steps that we're moving into. So as I mentioned, chip production hasn't standardized designs and architectures. Some chips are butt coupled, some require free space transmission. Some of the fibers are PM, all of the fibers are PM. It's kind of all over the place. Even some of the interfaces are staggered, some are linear. So there's designs out there that are kind of all over the place. The bottom line is we are trying to minimize insertion loss. So the insertion loss is coming from a lot of different directions, but the ability to lens, the ability to monitor skew, all of these things are leading into reduced insertion losses. So our goal is, looking at less than 0.5 dB of loss, and we're pretty close to that. We're also always looking at improved alignment technologies, particularly for our lensed and collimated fibers, being able to drop the lensed fibers directly into the waveguides through active alignment is critical. And a lot of our processing is reliant on in situ mode and far field matching. Again, that's the kind of the secret sauce for good coupling efficiency. So we're always looking at improving our in situ measurements. The ribbonization process that we spoke about is limited to about 1 meter in length. And again, working with our sister company, FiberCore, we're trying to achieve longer length ribbonization while maintaining PM alignment. Challenge, yes, every manufacturer of PM fiber has different beat lengths. So kind of keeping up with the beat lengths is certainly a challenge. The holy grail of any manufacturing process, be it a single mode connector line all the way down to an FAU production line, is of course full scale automation. We believe that we've got the steps, the semi-automated steps in each of the elements of our production that will eventually lead us into a turnkey automation setup. So I hope that helps. I hope you found that beneficial. And Adam, Alan, I think we're ready for Q&A.
Well, thanks, Duane, for that fascinating and insightful presentation. Really great to see the depth of innovation and capability coming from the team here at OpTek. Now let's turn to some of the questions that have been coming in from our audience. So the first one here, great talk. What's the type of laser used for stripping and cleaving?
Yeah, Eric, we don't get into too much detail on the laser and the optics. The truth be told, we do use a lot of different lasers. Some lasers work well at the ablation level, some work well at the thermal level. I will tell you that our cleaving systems are a combination of ablation and the thermal component, and that can be held, that stays true even for the stripping. But it's hard to give a direct answer on the laser that we use, because we do use different laser systems.
Fantastic, thank you. Another question just come in. How does OpTek's semi-automated fiber laydown process improve repeatability or reduce alignment time compared to manual methods, Duane?
Yeah, good question. So we've been tinkering with FAUs for 5 years. It's our approach historically was fairly manual. Then we started getting into the PM requirements, and it was a real struggle aligning each fiber under magnification, locking it into place with epoxy, moving to the next fiber, et cetera, et cetera. So OpTek's, patented PM alignment system it eliminates that. It allows us to take a gang of fibers, create the necessary either slow or fast axis alignment, and then lock it into place. And once that's done, the challenge is over. You ribbonize it, and now you can strip that back and drop it into any type of V groove. So the PM alignment process within OpTek is really, it's enabling a whole host of other FAU production opportunities for us.
Fantastic. Next question in, and there's a few waiting, Duane. What methods are used to ensure optimal coupling efficiency when aligning fibers to V grooves in FAU assemblies?
Yeah. So again, the industry's really settled for years on just flush polish. People are really good at polishing optical fibers, and that was great for DWDM technology, for butt coupling. You're really relying on the natural NA of these fibers for your transmission, and they were developing waveguides that were accommodating to these numerical apertures. The reality is, a lot of the chips that are being manufactured today in the world of silicon photonics aren't quite that accommodating for a variety of different reasons. And so the ability to put a lens or a collimator or some sort of structure on the end of that fiber that's going to feed the beam into or away from the waveguide is critical. So yeah, coupling efficiencies, the name of the game, low loss, critical, and the ability to build these FAUs with lensed or modified structures is helping with the coupling efficiency.
Great, thank you. What are the typical tolerances on the skew and divergence of the individual fibers in the FAUs?
Good question. So, a typical FAU, say a 12 fiber, it varies by fiber count. We build FAUs today that are 2 fiber. We build FAUs that are 24 fiber. They're all over the map. So yeah, the beam skew is basically a measurement against a detector. Let me take a step back. So the very first piece of this is going to be coplanarity. If your fibers are off by 50 microns from end to end, you're going to have various spot sizes entering into these waveguides. That's an inherent problem. Beam skew. Again, there's a lot behind beam skew, but fundamentally, if you've got cleave angle errors, you have introduced beam skew. Our laser cleaving processes are pretty dialed in. Most of the working distances that we're working with are in the tens to hundreds of microns, and we're able to bring the beam skew core to core skew, so it's negligible. It's we're looking at certainly less than a couple of degrees, which means the light is not missing the core.
Okay, fantastic, thank you. Another one here, Duane. What accuracy regarding fiber core position do you usually achieve? And do you also offer special PM fiber arrays with extra low tolerances?
So we're maintaining a half micron core to core. That's the specification. That's pretty industry accepted. In terms of what was the other part, Alan, with the PM?
The other one was, do you also offer special PM fiber arrays with extra low tolerances?
So extra low tolerances, perhaps we're talking PER. We do. Again, we're measuring PER, everything from 18 dBs up to 25 dBs. And it's just a matter of Six Sigma production to provide some sort of a price point. There's high, obviously the higher PER are slightly more expensive systems.
Okay, cool. A couple more. Can laser end capping techniques officially manage numerical aperture and mode field diameter for improved far field performance?
Yeah, absolutely. So when you slap a lens on the end of a fiber, you're really not manipulating NA or mode field diameter. You're basically just changing where that spot in waste occurs. If you're taking a single mode fiber and attaching elements of coreless fiber or graded index multi-mode fiber, then absolutely you're now, and each one of these segments is precisely cut down to the desired length that is governed mathematically by the optical design. And we're able to get those lengths down to within 5 microns. So you are able to take a 0.12 in a fiber and manipulate that to something else just through coreless attachment. Same with mode field diameter. Most of our end capping, or a lot of our end capping, is basically a poor man's way of achieving collimation through quarter pitch. And we've got good processes for achieving quarter pitches as well. So yeah, absolutely. Beam transmission can be modified.
Here's a really interesting one coming, Duane. How does laser stripping compare to mechanical or chemical stripping in terms of precision and induced stress on PM fibers?
Yeah, another good question. So thermomechanical stripping is far from precise. You're typically going to be in stripping a fiber or an array or a ribbon of fiber, and you're going to be then cleaving it back to the desired position. When you laser strip, you're able to get the endpoints down to within a few microns, very precise, with nice sharp shoulders. But thermomechanical methods of stripping that certainly imparts radial stresses. So if you're dealing with PM fiber, you're going to be contending with radial stresses that are going to affect the stress rod PER. Even with chemical means. So chemical is non-invasive, just like laser processing is fairly non-invasive. But with chemicals, you're typically using hot sulfuric acids that have a tendency, just because of the surface tension of the acids, they create pockets at the shoulders, kind of in between the cladding and the primary buffer. That recess has a tendency to swell, and again, you've got radial stresses that are now imparted. That's going to compromise PER. So laser processing, completely non-invasive, and there's no radial stress imparted on the fibers.
Fantastic, thank you, Duane. A couple more to go. How do you decide between flat and angled cleaving for different FAU designs, and what impact does that have on back reflection and insertion loss?
So again, chip designs today are all over the place. What's integrated? Typically you've got transmission source, you've got receiving sources. And then, are there isolators, are there circulators, or, what is built into the chip? So, basically if you have to know what the fiber is being interfaced to in terms of the waveguide. So certainly if these are transmissive legs, you're watching out for back reflections, in which case, maybe they're angled, maybe they're not. If these are receiving legs, it's probably agnostic to whether it's angled or not. But one thing is for sure, no matter what we're doing to the end of these fibers, flat, cleave, lens, ball lensing, one thing is for sure, the beam skew, improper, poor coplanarity, all of these things are just going to be magnifying losses. So, if you're able to achieve, tight coplanarity, minimal skew through well-defined angle control, then your losses are going to be minimized.
Brilliant, thank you again. Last one, how is birefringence preserved during laser processing of polarization, maintaining fibers like panda and bow tie designs? Excuse my pronunciation there, Duane.
Yeah, that's another pretty loaded question. So laser, again, you could almost write a PhD on this, but laser processing, you're coming in with the beam. There's a combination of ablation. There's thermal energies, but at the end of the day, you're really not. It's a gradual release of the pent-up strain. When that fiber is drawn, there's strain in it. You've got boron-doped stress rods. That's what's creating the birefringence, is the stress rods. So, a laser comes in, it's a gradual and almost an annealed release of any type of pent-up strain. When you mechanically cleave or introduce any type of blade to the cladding of a fiber, there's stress propagations all the way through, and that pent-up strain is the energy is going to be released in such a way where you could, I like to say you will, but you could lose a lot of your birefringence between that pent-up strain between the boron-doped stress rods and the clad. So basically, it's a gradual release of the strain energy versus an abrupt release of the strain energy.
Okay, I did say that was the last one. I've got a couple more come in. If you're okay to keep going, Duane.
Absolutely.
Is it possible to cut the LDF such as 400 microns?
Yes, we do that every day. We have systems in place that will cleave large core fibers up to 1 millimeter, 1.2 millimeters.
Okay. Fantastic. And the last one, what are the primary challenges in processing 80 micron fibers compared to standard 125 micron fibers during ribbonization or termination?
Yeah, another good question. So again, we believe that there will be a push towards 80 micron. It's smaller. 80 micron processes from a laser stripping and laser cleaving perspective, they're going to process the same as 125 micron. The difference really lies into the materials. To bring dicing systems today, dicing blades, they're beautifully set up for 125 micron V grooves. The 60-degree angles of the V grooves, dicing is set up. You've got 127 micron to 250 micron pitch spacing, again, well established. So I think it's a matter of bringing in an awareness and a shift in the industry towards developing the materials that will accommodate 80 micron fibers.
Okay, and I keep saying it's the last one. We've another one come in. Duane, are you offering aligned PM ribbons, not finished arrays, for contract manufacturing as well? And what will be the minimum amount to order?
Yeah, again, so we do not offer PM aligned ribbons. We spent a fair amount of development time. We've got patents around that alignment process, and we're currently using the ribbons for in-house production. Now, time will tell. I suspect eventually we'll be building modules. Again, half our business is building equipment for fiber production. So I think it's only a matter of time before Alan and his brain trust have fully automated PM FAU-based systems that would include the ribbonization.
Fantastic. I'm just scanning last time. No more questions in. So that's it for today. We really hope you enjoyed our third OpTek webinar. A big thank you to Duane for a great presentation and sharing his insights with us and answering all of those questions, Duane. It's really been interesting. We'll be uploading the recording in coming days, and we'd love you to join us for our next session, laser processing of optical fibers and components, on Wednesday, the 5th of November at 4 o'clock GMT with Chris Randon, OpTek's Business Development Manager here in Abingdon. So thanks again for joining us, and we do hope to see you next time. Thank you.